Alright everyone, here we go. We are back today looking at logarithmic functions. Hope you've grabbed your calculator, you've got your handy colored pens. Let's start off by talking about a function and a one-to-one function. So if we want to look at our most common function, the one that we've worked with the most is probably our quadratic function, right? F of x equals x squared. Now we know this is a function by looking at the graph because each x has a unique y value. If I plug in 2, I get out 4. If I plug in 1, I get out 1. There's only one answer, so each x has only one y. Each x has only one y value, and it passes the vertical line test. If we're looking at the graph, it passes the vertical line test. I can draw any vertical line I want, and it will only ever pass through my function one time. Well, I can invert anything, but if I want a function whose inverse will also be a function, I have to start out with a one-to-one function. Well, a one-to-one function is a special type of function. It's still a function, but this time each x value is assigned to or results in a unique y value. Each x value has a unique y value. This quadratic function here, each x is assigned to only one y, but 2 squared is 4, and negative 2 squared is also 4. So I repeat my y values. This quadratic function is not one-to-one. A one-to-one function will pass the vertical line test. It will also pass the horizontal line test. If I draw a horizontal line and it's one-to-one, it will only intersect the function in one time. So this function is not one-to-one. However, our exponential functions are one-to-one. If you look at a quick sketch of our exponential function, our parent or base exponential function, if we just say f of x equals a to the x power, any base is going to have, for the parent function, is going to have that horizontal asymptote at y equals 0. It has that y-intercept at 0, 1. It passes my vertical line test, and it also passes my horizontal line test. Now this tail end over here looks like it gets horizontal, but remember that that's a fraction that's getting smaller and smaller and smaller. It's getting closer and closer and closer to that horizontal asymptote as I go, x approaches negative infinity. This passes my horizontal and my vertical line test, so my exponential function is a one-to-one function. So the inverse of my exponential function is still a function. The inverse of my exponential function is a log function. Now how do we find the inverse of a function? Hopefully you remember we did the switch and solve method where you switch the x and the y and then you solve for y again. Another way to look at this is that you exchange the domain and range. The domain of one function is the range of its inverse. So if I have this value, for example, is at 0, 1, that means that on its inverse, the inverse function, the logarithmic function, is going to contain the point 1, 0. In fact, this is what my log function looks like. Suddenly I have a vertical asymptote at x equals 0. I've reflected my original function, my exponential function, across that line, y equals x. Alright, I just did all that up here, and we're going to set it down and do it base 2 here. So let's line this out. If you remember, whenever we're trying to graph an exponential function, we start with 5 basic x values. -2, -1, 0, 1, and 2. That's the easiest way to find our horizontal asymptote and our exponential increase or decrease. If we are base 2, then 2 to the -2 power is that 1/4. 2 to the -1 is 1/2. Anything to the 0 power is 1. There's my intercept. 2 to the first is 2, and 2 squared is 4. Alright, so coming down here, this is my exponential function. We've got that y-intercept, 0, 1, 2 to the first power, 2 to the first power is 2, 2 squared is 1, 2, 3, 4. There's our exponential increase. If I have -1, 1/2, then 1/4, and I am approaching that horizontal asymptote, moving back toward -infinity. So there is f of x equals 2 to the x. The domain of this function is all real numbers, and I have a limit on the range. My limit is my horizontal asymptote, so from 0 to +infinity. Now we want to find the inverse of that. The inverse is the log function, base 2. And to find the inverse, we're going to switch the domain and range. So for the inverse function, the log function, now the domain is all real numbers, and the range is going to be from 0 to infinity. My log function, instead of having a horizontal asymptote that limits the range, now has a vertical asymptote that limits the domain. So I'm going to have a vertical asymptote at x equals 0. The easiest way to graph a log function is to start with the exponential function and then switch the domain and range. So my x column for my exponential function becomes the y column. The y column for my exponential function becomes the x, or the domain, column for my log function. Okay, so notice that all of my x values are positive. They're greater than 0. My first value, x to the 1/4, is at -2. X to the 1/2 is at -1. X is 1 is at 0. And then I've got 2, 1, and 1, 2, 3, 4, up to 2. That was a little high. There we go. And there's my log function. The log function and the exponential function reflect across the line y equals x, because every function and its inverse reflects across that line y equals x. This is g of x is equal to log base 2 of x. Now, if you think about our work with exponential functions, you know that when I change the base, it doesn't change the general shape, it just changes how steep it would be. So if this was base 3, this would be a steeper curve, and that would flatten out faster when I flip it and make it the inverse, the log function. Another good important piece of information to remember as we're working with log functions is that the answer to the log function, if I have a log function problem, the answer to the log function is always the exponent of the base. Now I have 3 basic pieces of information that I'm interested in. I've got a base, an exponent, and an argument. I define a logarithm by simply saying that if I have a log statement, I can switch it with an equivalent exponential statement. These two statements are equivalent to each other. They mean the same thing. They will get me the same values. All I'm doing is rearranging those 3 pieces of information, and I can switch back and forth. Now this allows me to get the variable in a location where I can solve for that unknown variable, solve for x. Alright, let's look at the next page. Remember, you guys can always pause me and rewind. That's the beauty of having this on a video. So as I said, when we're dealing with exponential and logarithmic functions, there are three pieces of information that can switch back and forth, switch places when you're converting from an exponential function to its inverse logarithmic function. When I'm switching back and forth from an exponential function to a logarithmic function, there are three pieces of information we're interested in. First, I have a base. If I'm in exponential form, that base is raised to an exponent. And when I multiply that out, the base raised to the exponent yields an argument, or kind of a product, right? So, for example, if I wanted to look at an example of this, one that you're familiar with, 2 cubed, there's my exponent, is equal to the argument 8. Because 2 cubed is 2 times 2 times 2, that gives me 8. So there's my three pieces of information: base, exponent, argument. When I rearrange that and put that in log form, my equivalent log form, so these have the same values. My base of the exponent is the base of the logarithm. Now remember I said that the answer to the logarithm is the exponent? That shows up right here. My base is the base of the logarithm. The answer to this log equation is the exponent. And that means the only piece of information left to put in is that argument. So what would this look like? Well, I would have log, my base here is 2, base 2. The answer to the log statement is the exponent. So the answer to the log statement is that 3, and the argument goes here on the left side of the equation in this case. So I would read this as log base 2 of 8. Log base 2 of 8 is 3. The question I would ask myself with this: what is the exponent of 2 that gives me 8? Because I know this is the base. What is the exponent of 2 that gives me 8? Alright, so we're going to practice this. I've got three different equations. These are all in exponential form. You have a base with an exponent. And we're going to turn it around and write each one in logarithmic form. So all we're doing are rearranging those values. I've got 4 to the negative 3 equal to 1 over 64. So 4 to the negative 3 is equal to 1/64. Sorry guys, I'm trying to get that a little clearer. My base is 4, so log, and then my base is written small, down there is a subscript, of the argument. My argument is 1/64. That's why I have my erasable pens today. 1/64 is equal to the exponent negative 3. What is the exponent of 4 that gives me 1 over 64? Well, that exponent is a negative 3. Alright, let's go to the next one. I'm writing this equivalent log statement. My base here is 6,561. My argument is 9, and the answer is the exponent. In this case, the exponent is 1/4. What is the exponent of 6,561 that gives me 9? Now notice that I went from a large value to a small value. That means that I took a square root, cube root, fourth root, some kind of root, and that root as an exponent, you remember our rules for exponents, is going to look like a fraction. So I end up with a 1/4. If I plug that into my calculator to check, make sure that it works out, because these are all correct problems. I don't have a log any base button, so I can't work it as a log statement, but I can check it as an exponential statement. The fourth root, so I need to put in my 4 as my index, get that glare off, put the 4 as my index, then do the exponent button, second function, so the fourth root of 6,561 is 9. I could also say 6,561 raised to the, and then I need to open parentheses, 1/4 power is 9. Those are two equivalent ways to do that. And then we know, of course, that anything to the 0 power is 1. This base here is 5, so the equivalent log form, log base 5 of 1 is equal to 0. Anything to the 0 power is going to give me an argument of 1. So anytime you have an argument of 1, you know your answer is going to be 0. We didn't talk about this negative exponent here. When I have a log statement where I have a base and then I have the reciprocal of that base, suddenly that base raised to a power is in the denominator, I know my exponent is going to be negative. Log base 4 of 64 would be a positive 3, because what is the exponent of 4 that gives me 64? What is the exponent of 4 that gives me 64? Well, that would be 3. So if it's 1 over 64, my exponent would be a negative 3. Alright, let's look at going back the other direction. Now we've been given a log statement and we need to write it in its equivalent exponential form. So we're just working the other direction. So my base is 2. Remember, the answer to the log is the exponent, and there's my argument 8. 2 cubed is 8. Now these problems you can check. I know that 3 to the 4th power is 81. That makes sense to me. Base, exponent, argument. So I can check and think through, did I get things in the right place? When I get to something like this with just variables, I have to know what piece of information goes where. My base, my answer to the log statement is my exponent, and that's equal to that argument x in this case. A lot of what we're doing, practicing to switch back and forth from log form to exponential form, leads us into solving equations with logarithms. So make sure you get comfortable doing that switching back and forth. Always remember that the answer to my logarithm is the exponent of the base. So for these equations, I'm looking for an exponent that's going to make this true. So for this first one, what is the exponent of 3 that gives me 9? Now while you're working this out to get comfortable with this, if you need to write it like this and say, okay, I've got base 3, I'm looking for an exponent, I end up with 9, in order to figure out that that would be 3 squared, that gives you 9, my exponent is 2, do it, go for it, write that over on the side. Again, right here, what my base is 5, I'm looking for an exponent that's going to give me 625. Well, 5 to the 4th power gives me 625. Something else that is helpful, the other day we did that exponent page where we raised several numbers to different exponents. If you know your base is 5, just go through and say 5 times 5 times 5 times 5 and see how many times you have to multiply 5 times itself to get 625. Same situation here. What is the exponent of 6 that gives me 216? 6 times 6 is 36 times another 6 is 216. So that exponent would be 3. Number 4 looks a little different. This time my base is larger than my argument. We had an example like that up here where our base was larger than our argument. Let's go find that. Where did we do that? Where our base was larger than our argument, right here. In log form, my base is larger than my argument. My answer was a fraction because I had to take a root. So here, my base is larger than my argument. So I'm going to think, okay, what root of 9 gives me 3? What should that index be? Well, it's the square root of 9 that gives me 3. And square root is the same thing as the exponent 1/2, where 2 in the denominator is my index. Let's look through. I don't see any others like that where my base is greater than my argument. Oh, let's look at this one. This is an interesting one. What is the exponent of 2 that gives me negative 4? 2 to the what power is equal to a negative 4. Well, 2 squared is 4, but there's no exponent that I can raise 2 to get a negative value. Do you remember in our definition of exponential function, we had restrictions on a, what a could be? We still have those same restrictions here. Our argument's never going to be negative because we always have to start with a positive base. So that is just not possible. You could also say D and E for does not exist. That one's not going to work. What about this one? What is the exponent of 3 that gives me 0? Now, if I raise anything to the 0 power, I get 1, But is there any power that I can raise something to and get 0? Nah, that one does not exist either. That's not possible. All right. Number 7 looks familiar. We had a problem like number 7 up there, where we started with a whole number as our base and a fraction as our argument. Log right there. Whole number base, fraction argument. I had a negative exponent to make that happen. So I know that 2 squared is 4. So 2 to the negative 2 is 1/4. 2 to the negative 2 power is 1/4. Again, write that off to the side if you need to help you out with that. Oh, this is fun. I've got a fraction in my base, and a whole number is my exponent. Well, I'm still taking a reciprocal and raising to a power here. I know, for example, that 2 cubed is 8. If I just cube this, though, it would be 1/8. To get that flipped, I have to make my exponent negative. All right, one more here we'll do together. What is the exponent of 4 that gives me 1/16? Well, 4 squared is 16. To make that flip, to make it take the reciprocal, I have to make it a negative exponent. All right, I'm going to hush for just a second, let you guys answer these last 3. I will put the answers up. If you haven't thought through them, pause the video, finish through 12. If you didn't get the right answers and you don't understand why, go back and rewatch what we've just talked through. If that still doesn't help, contact a math tutor or contact me, or get in my math lab and watch some additional videos and do some practice problems with that. All right, we're going to move right on. There isn't an any base log button on your calculator. There isn't. We've got log log and ln. Those are the 2 bases that we have. And if you look right above, you can see which base each of them refers to. You can evaluate logs in 2 special bases using your calculator buttons. Our common log is what we call this top button, log. And you can see right above it, the second function is 10 to the power. That's the inverse. So common log is base 10. And like I said, that's that log log button. Natural log, ln, I think it's in French, why they abbreviate it ln. If you look right above, it is base E. Base E is my ln button, natural log. Those are the only 2 bases that you can just plug things into your calculator for. Now, common log, some things are pretty easy. We don't have to use our calculator for them. For example, if I have a power of 10, if I have log log written with no base down below, I know that is a common log. That's how I know I'm dealing with base 10. Well, what is the exponent of 10 that gives me 1,000? All you have to do is count the zeros, guys. So these are super easy. I've got 3 zeros here, so that means 10 cubed is 1,000. 3 zeros, exponent 3, 3 zeros. So my exponent here is 3. What's the exponent on 10 that gives me 100,000? Well, count your zeros. Now this one is a decimal. That's tenths, hundredths, thousandths. So 1/1,000. Remember, when we end up with that reciprocal, we're dealing with a negative exponent. We've got 3 decimal places, -3. Now, not all common logs are going to be powers of 10. I could ask you to find the log of 7. This is still base 10, but the question is, what is the exponent of 10 that gives you 7? That is not going to be a nice round integer number. So I'm going to have to come over to my calculator, and I'm going to have to say common log, and then I want the common log of 7. It has to round it off when it runs out of room. When I use these buttons, unless it's a special case like one of these, it's always going to give me an irrational solution. So pay attention to my math lab. It usually tells you to keep several decimal places. If I keep 4 decimal places here, that would be 845, and then this 0 is going to round up. So 0.8451 would be the common log of 7. All right, we could do these without our calculator. We had to do our calculator for this one because 7 is not a power of 10. We knew these were all common logs because it was log with no base written. It was just log with no base written. Oops, with no base written. Sorry, with no base written. If it's log and the base is missing, you know that means it's base 10. If it's natural log, ln, then it also does not have the base. But because it is ln, you know it is base e. Now, these two are going to give us special cases. What is the exponent of anything that gives you 1? So we don't even have to do that in our calculator. The exponent of anything that gives you 1 is 0. If you wanted to do that in your calculator, you absolutely could, just to practice. Natural log of 1 is 0. What about natural log of 10? Now 10 is not one of our a special value for base e. So natural log 10, notice that goes all the way off. Let's round that to, it says 3 decimal places. So we're going to do 0.30, and then that one, because I look to the right, is at least 5 or more, so it rounds up, so 2.303. Take a look at that next one. What do you think's going on there? Hopefully you recognize that we have a negative argument. When we have a negative argument, that is not going to work. That does not exist because of that negative argument. There is no exponent I can raise a positive value to that's going to give me a negative argument. Now, how did we know these were all natural logs? We knew these were all natural logs because we had ln written. So we know that that is going to be base e. Now, there is not an any base button on your calculator. One more time. There's no way to just hit a button and solve base 3, base 5, base 4, whatever, other than e or 10. So what do we do if we need an approximate answer to a logarithm that has a base other than 10 or e? Well, we have a change of base theorem for that. Our change of base theorem says that as long as a is a positive value, not 1, then we can rewrite it as a ratio. Because anything as a ratio, those units divide out. Think about if you were going to clean with a concentrate. This is my example over here. If you had a concentrated cleanser and the instructions on the cleanser say 1 part cleanser to 3 parts water. 1 part cleanser to 3 parts water. And that PT, I just mean part. Well, if I just want to clean up my counter, I may do 1 tablespoon of cleanser to 3 tablespoons of water. And I'm just going to make a little bit. Or if I need to do my floor, I might do 1 quart of cleanser to 3 quarts of water. And then I make a bucket full. But no matter what units I use, because I'm doing a ratio of parts to parts with the same value, those units end up dividing up, and I have the same strength for the cleanser. The same is true if I'm using my natural log or common log. You could use either log button and do this. What's important here is that this base goes in the denominator. So remember that the base goes on bottom. When I set up my ratio to use the change of base theorem, the base goes on bottom. All right, let's practice some of these just to see what we're talking about. So for this first one, I want to find log base 3 of 56. I don't need an exact answer. There's not a nice exact integer value that's going to give me this. There's no exponent of 3 that's a nice integer that gives me the value 56. So I'm going to use my change of base property, and I'm going to round my answer to 2 decimal places this time. Now, change of base property, because there's no base 3 button on my calculator, 56 goes in the numerator, the base goes on bottom. So that's what I'm going to do in my calculator. And I could have done common log button. It really doesn't matter. All right. So here's what this looks like. Natural log of 56, and then I hit enter. Or you could close your parentheses and keep going. That's fine too. But either way, we're not going to round it off. This value is divided by natural log of 3. Enter. And there's my result. Remember I said to round to 2 decimal places. So we're going to round this off. We're going to say approximately 3.66. Wavy equal sign means approximately. All right, let's look at this next one. My base here is 0.2 2/10. So I'm going to do common log button here. Common log of 9 over common log, base goes on bottom, 0.2. And that's what I want to work out. So in my calculator, I'm going to choose to do the common log button of 9. I'll go ahead and do it all in one go this time. Close my parentheses, divided by common log of 0.2, close my parentheses, and I get a negative value. That's fine. My exponent is negative because my base is smaller than my argument. I've got a negative 1.37 rounded to 2 decimal places. Those exponents, remember, can be negative. It's that base that can't be negative. All right, numbers 3 and 4 are not in log form. They're in exponential form. That variable is in the exponent. We cannot solve for a variable in the exponent. We have to do something to get the variable out of the exponent in order to be able to solve. The way that we're going to do this is to rewrite this, use our definition of logarithm, rewrite this in the equivalent log form. So log of the base here is 5.44, the argument, 2.3, is equal to the exponent. Now we have solved for x, well, we've set it up to solve for x. We couldn't solve for x while it was written as an exponent, but we can solve for x here in log form because the answer is the exponent. Now there is not a base 5.44 button on my calculator, so I've got to set up either common log or natural log. It really doesn't matter which one you pick, as long as you hit the same button in the numerator as you do in the denominator. So I just switch back and forth in my notes to remind you that either one works. You can stick with one all the time. It doesn't matter. But which of these two values goes in my numerator? Well, the argument, 2.3, goes up on top, and the base, 5.44, goes on bottom. And when you plug that into your calculator, you should come up with, rounded to 2 decimal places, 0.49. Remember, either do natural log of 2.3, enter, or close those parentheses before you divide by the natural log of 5.44. One last practice problem here. Rewrite this as log form because we can't solve it with the variable in the exponent. My base here is 10, so that means I get to use my log button. Log base 10, I don't have to write the base. Argument is 3.91, and that is equal to the exponent, x. And this I don't have to use change of base for. This time I can just do my log button, 3.91. That should give you an answer rounded to 2 decimal places of about 0.59. So log button, log log, is base 10, 3.91, rounding to 2 decimal places. How did I know I could just use my common log button? Base 10. And when I wrote it, I didn't write the 10 as a base because it's understood. Just like when I do a radical, a square root, my index is understood to be a 2 unless I write a different index. Now there are some general properties of logarithms that come from that definition of logarithm that if you can remember, it's going to make your life a lot easier. We've set up, reminded ourselves that, oh yeah, a has to be positive and can't be 1. That r that I'm plugging in here can be any real number I want it to be. All right. My first property for logarithm from the definition says that any value raised to the 0 power is 1. So a, any base, of 1 is going to be an answer 0. For example, an example for A, I can plug in any number I want to down here for this base, as long as it's a positive value, not 1. And I put a 1 right there. No matter what this base is, if my argument here is 1, the answer is 0, because 0 is the exponent that is going to make any base equal to 1. All right, what about this second one? I'm saying, all right, A to what power gives me A? Well, 1. Anything raised to the first power is just itself, right? So B says that if I start with something that looks like this, what is the exponent of 7 that gives me 7? That answer is always going to be 1. Now, it doesn't have to be a number. Understand, I could tell you, all right, log m of m. Well, what is the exponent of m that gives me m? It's going to be 1. So anytime the base and the argument match, the answer is 1. Anytime the base is given an argument of 1, the answer is 0, because those are my rules for exponents. Now, C and D get a little more complex. Take a look at those. And think about what the question is here that we're asking. What is the exponent of A that gives me A to the R power? Now, remember I told you to kind of write those so that it makes sense to you. So if I wrote this out on the left, I would say, what is the exponent of A that gives me A to the R power? Well, my missing piece is that exponent R. So, therefore, that little triangle right there just means therefore, if I have log base 5 of 5 cubed, what is the exponent of 5 that gives you 5 cubed? Well, that exponent would be 3. So I'm looking for that exponent given back to me. D is the same statement, except now it's in exponential form instead of logarithmic form. A raised to the power log base A of x, the result is always going to be x. So an example of that, if I say 2 raised to the power log base 2 of 64, the answer would be 64. Okay, if you can remember these powers, it's going to make life a lot easier moving through and working with exponents, because you'll be able to just kind of answer some questions quickly that you won't have to work out. Okay, remember that logarithms are the inverse of exponential functions. What this means is that we have more properties for logarithms, and those properties for logarithms are going to be related to our rules for exponents. This bit is not new. This is something that we reviewed at the beginning of the semester. We're going to review it again now really quickly so that you can remember. The product rule for exponents is that when you are multiplying the base, you add the exponents. And here in generic form with variables, b to the m times b to the n equals b to the m plus n. What does that look like with numbers? 2 cubed times 2 to the 4th. I'm multiplying the base. The base is the same. I just add the exponents and I get 2 to the 7th. The quotient rule for exponents says that when you're dividing the base, you subtract the exponents. Now, I know we've talked about this before. Multiplication is just repeated addition. Division is just repeated subtraction. So if I'm dividing the base b, I subtract the exponents to figure out what that should be, what my power should be. So let's do this with our 2's again. If I have 2 cubed divided by 2 to the 4th, well, that's the same thing as 2 to the negative 1, because 3 minus 4 is negative 1, and I don't ever leave a negative exponent sitting there like that. I take the reciprocal, so that's 1/2, which is what we would expect, because I have 3 2's in my numerator, 4 2's in my denominator. 3 of those 2's are going to cancel out, factor out, and I'm left with the 2 in my denominator. My final rule, my power rule for exponents, when I raise an exponent to a power, that's when I multiply the two exponents. Now this looks different from my product rule. because my base is only written one time. I have a base raised to a power, raised to another power, and that's when I just multiply those exponents together. So instead of 2 cubed times 2 to the 4th, I would be doing 2 cubed raised to the 4th power. I only have the base written one time. You see the difference there. When it's like this, I multiply the two exponents together, and I would get 2 to the 12th. Alright, we're going to use these rules for exponents to help us expand and condense log statements so that we can sometimes simplify the expressions. Sometimes they just give you practice problems to work with. Sometimes it actually helps us to simplify and break things down and solve. Okay, our product, quotient, and power rules. Just like we had product, quotient, and power rules for exponents, we have product, quotient, and power properties or rules for logarithms. The product property tells me that if I am multiplying in the argument, I break that apart as addition so that x times y is my argument. I now have two log statements. One is with x as the argument, the other is with y. Multiplication pairs with addition. Now it works both directions. If I start with two log statements like this and I'm adding the two statements, I can write it as a single logarithm where the arguments are multiplied together. The quotient property, remember that division is paired with subtraction. So I can break this division and the argument apart and show that I'm subtracting anything that was in the denominator. Or if I start out by subtracting, I can put it together as a division in the argument. And then finally, my power property. If I'm raising an argument to a power, I can move that out in front and show that I'm going to multiply it times the log statement. Just like I raise an exponent to an exponent, I multiply. If I raise an argument to a power, I pull that out front and multiply. Alright, let's see how we can put these into practice. Number 1, we have log base 3 of 27 over 4. So in my argument, I am dividing. Division, quotient property, pairs with subtraction. So I'm going to pull that apart and write it as two separate log statements, base 3, where I am subtracting whatever was in the denominator. So log base 3 of 27 minus log base 3 of 4. And then I stop and think, okay, can I simplify either of these statements? Is there an exponent that I can figure out? Well, yeah, right here. What's the exponent of 3 that gives me 27? Well, 3 times 3 times 3 is 27. So log base 3 of 27 is just 3. I can't simplify log base 3 of 4. So that's as simple as we can get that. But whenever I can simplify something, I want to go ahead and do that. Alright, we got a lot going on in this argument. We're multiplying, and then we've got a power to that x. We're going to start with our product property. In my argument, I have 3 times x squared times y. So I can pull that apart to 3 separate natural log statements. Multiplication, product, property, pairs with addition. So natural log of 3 plus natural log of x squared plus natural log of y. And then because I've got this exponent here, I can apply my power property and bring that 2 out front. Now notice I'm only squaring the x, so this middle statement is the only one that gets a 2 written out in front. And I can't simplify any of those, so this was just a practice problem. I can't actually simplify anything there. Alright. We have several problems to practice here. We're going to pull things apart on numbers 3 through 9, and then we're going to turn around and go back the other direction for 10 through 14 and condense our log statements into a single expression. First property I see I can use here is my power property, so I can bring that x out front and say x times log base 3 of 9. And then And then this piece I can simplify. What's the exponent of 3 that gives me 9? Well, that's 2. So I have x times 2, which we would just write as 2x. Alright, this is another example of when I can use my power property. I need to rewrite that radical as an exponent. This is square root, so the index is 2. So this is log of 3 to the 1/2 power. The index, the radical, square root becomes an exponent of 1/2. Now I don't have a base written, but it's log log, which means I'm in base 10. I can use my power property again and bring that exponent out front. Common log of 3, well 3 is not a power of 10, it's not 100 or 1,000 or 1,000,000, so I can't go ahead and simplify any further. Alright, number 5, common log, base 10, because the base is not written and it's log. I'm multiplying in my argument, multiplication pairs with addition, so I can use my product property to split this apart into 2 separate log statements. Common log, base 10, don't have to write the base. This first one can be simplified. My base is 10. What's the exponent of 10 that gives me 100? Well, 100 has 2 zeros, so 10 squared is 100. That simplifies to be 2 plus log x. Number 6 is going to use your quotient property because you're dividing. Division pairs with subtraction. Go ahead and pull that apart and write it down as a difference of the logs. And then stop and take a look at it. We've got 2 separate statements. The denominator, the bottom, is being subtracted from the numerator. This statement can be simplified. What is the exponent of 4 that gives me 64? Well, 4 times 4 is 16 times 4 is 64, so cubed. That statement simplifies to be 3 minus log base 4 of y. So sometimes we can simplify things, sometimes we can't. We do our best to simplify anywhere we can. Unless we're told to approximate, we never go ahead and like I wouldn't use my change of base formula here, or I wouldn't use my calculator here to find log base 10 of 3 because I wasn't told to approximate the answer and round. Alright, property here is the product property again because I'm multiplying, and I know that multiplication pairs with addition. And when I take a look at this, neither of these is going to simplify. There's no exponent of 5 that gives me 7, and m is a variable, so I for sure can't figure anything out with that. Do note that I'm writing the base small as a subscript, and then the argument is large as the log statement. That is the proper form, so make sure that you're writing these correctly as you go through. Alright. In my argument, I have a quotient, and I'm going to have a power rule, but let's apply the quotient rule first. So I have natural log of e to the 5th, that's my numerator, minus the denominator, natural log of 11. In this first statement, I can apply that power rule and bring that 5 out front. The 5 is only applied to that numerator part, the natural log of e, because I'm not raising the denominator to the 5th power. And then right here, what's my base for natural log? Well, it's base e. What is the exponent of e that gives me e? It's 1. 1 times 5 is 5. So 5 minus the natural log of 11. Try to make it so you can tell when I'm writing natural log and when I'm writing ones. Natural log of e, exponent of e that gives me e is just 1, and 1 times 5 is 5. Alright, number 9. Again, we've got a radical. Remember that when you have a radical, you're going to rewrite that radical as a fractional exponent. This time we've got a cube root, so we've got an exponent of 1/3. That's the only thing going on, so we're going to use our power rule and pull that power out in front. 1/3 of the natural log x, and there's not anything else I can do with that. That's as far as I can take it. Okay, that was all expansion. We were pulling things apart. Now we are going to condense some logarithms. We're going to put things back together. So we're going to condense each statement to a single expression, and always simplify if you can, but I'm not told to round, so I'm not going to pull out my calculator for this. Alright, I'm adding the two log statements. Addition pairs with multiplication. So I'm going to multiply the arguments together. Log of 25 times 4. Well, what's my base here? It's not written. Log, no base written, is base 10. 25 times 4 is 100. So what is the log of 100? Well, base 10. What's the exponent of 10 that gives me 100? 2. I can't simplify them when they're split apart, but when I condensed it into a single log statement, I was able to get a solution. I was able to simplify all the way down to 2. Now, not all of these are going to simplify. In fact, none of the rest of these I think is going to simplify. Now we're just practicing putting our rules to practice. So we got a lot going on here. Now I want to point out to you that when I am adding in an argument, I do not have a rule for adding in an argument. There's no way to separate that out. My rules are for multiplying in an argument or dividing in the argument, not for addition in the argument. So what I've got going on here first is this power rule. And we're going to do that first. So natural log of x squared plus natural log of x plus 5 to the 1/3 power. And then I see that because I'm adding two log statements with the same base, I can write that as a single log statement, and I can multiply the arguments together. So it's natural log of, and then I'm going to multiply my arguments together, x squared first, and then I'm going to go ahead and rewrite this, interpret this as a radical. I've got the 1/3 power, so that's going to be a cube root of x plus 5. Alright. On the next one, we're going to start with our power rule, work our way backwards. We have natural log of x plus 6 to the 4th power minus natural log of x cubed. Now I'm subtracting the two log statements with the same base. What does subtraction pair with? Subtraction pairs with division. So numerator first minus anything that's being subtracted goes in the denominator. Natural log of numerator over denominator, x plus 6 to the 4th power over x cubed. Make sure that your powers, your exponents, are in the right spots. Alright, number 13. Ooh, 3 separate log statements. Let's deal with those powers first. So I'm adding these two together and then subtracting. So I've got product rule, quotient rule. Anything being subtracted goes in the denominator. Anything being added up here in front goes in the numerator. Everything is natural log. So I set up my quotient in my argument. My numerator is going to be x cubed y to the 5th, and then I'm subtracting out that z to the 6th, so it goes down as the denominator. Final one, we've got 4 log statements. The first two are being added, the next two are being subtracted, so this is going to be numerator, denominator. I want to take care of powers first. Anything that has a power. And then I want to set it up as my single natural log with an argument. The numerator is going to be 3x squared because those are added together. The denominator is going to be y cubed z to the 4th because those are being subtracted out. Alright, excellent, excellent. We are almost done. We're just going to look at some transformations of graphs. And by now, hopefully, you are getting comfortable with our pattern of transformations. It's the same for every type of function. My pattern of transformations, and I'm going to write it out as a logarithm pattern here. Let's just say y is equal to, I could have a negative and a coefficient out front. Don't have to have a coefficient out front. Log base a. My horizontal shift is always attached to the x. Vertical shift is tacked on. This could be added or subtracted at the beginning or at the end, doesn't really matter. But just remember, this is my vertical shift. It goes up if it's positive, if it goes down if it's negative. This is my horizontal shift, left or right, and remember that this kind of goes opposite the way you think, because if I have x minus 3, that means I plugged in a positive 3, so that would go to the right 3 units. Any negative out front is going to reflect across the x-axis. Any coefficient would be a vertical stretch or shrink. None of this is new. We've been doing it all semester. That pattern of transformations. This is the same pattern. This is just what it looks like with logarithms. Alright, so we are going to look at our pattern of transformations for logarithms. We are base b. This is our parent function. This is our parent function. F of x is log base b of x. Base b could be any base, it doesn't matter. I've got a vertical asymptote right here, vertical asymptote at x equals 0. And I have an x-intercept at 1, 0. Those are my two pieces of information that I'm going to shape my transformations with. This is the shape of my log function right here. Goes through this x-intercept with this vertical asymptote at 0, x equals 0. Now let's do some transformations. Alright, if I have this function that I want to graph, what is this transformation that I've got going on from my parent to this function? Well, that negative out in front tells me to reflect across the x-axis. So let's see what's going to happen. If I'm just flipping it upside down, I'm not moving it left or right. So this vertical asymptote is going to stay at x equals 0. It's not going anywhere. If I'm flipping it upside down, this x-intercept isn't going to have to move. But, and this is how I think through it. I think, okay, so where this tail goes down, if I flip it, now that tail is going to go up. And where this curve is above the x-axis, now that curve is going to be below the x-axis. So let's think about domain and range. Up here for my parent function, the domain had a limit. My domain was from 0 to positive infinity, but my range did not. My range is all real numbers. That's the parent function. What about down here for this transformation? Did either of those values change? Well, all real numbers is all real numbers. It never changes. My domain has a limit of 0 for the parent. Because I didn't have a horizontal shift, that limit did not change for the transformed function. Exponential function has a y-intercept, but log function has an x-intercept, and our x-intercept is at 1, 0. It didn't move. All right, let's look at the next one. Our next graph, our transformation that we're interested in, right here, tacked on at the end. If you look at your pattern of transformations, that's my vertical shift. We're shifting up 3 units. And then I go in and I think, okay, well, what is it exactly that I'm shifting? If I'm going up, then that vertical does not move. It stays right where it is, vertical asymptote at x equals 0. If I'm going up, this y-intercept, not y, this x-intercept at 1, 0 from my parent function, not looking at the previous transformation, looking at the parent function. This good grief, this x-intercept, I'm so sorry, this x-intercept goes up 1, 2, 3 units. It doesn't move left or right, so the x-coordinate is still 1, but then it goes up 1, 2, 3, so that point, that becomes 1, 3. And I can draw my curve at this point. Did my domain change from the parent function? Well, no, because I still have the same vertical asymptote. So my domain is 0 to infinity. Range, all real numbers, stays all real numbers. Now my x-intercept happens when y is 0, right? I still have an x-intercept right there. And I know that my x-intercept is going to be between 0 and 1 because of the shape of my log function. To find an x-intercept, I set y equal to 0. So right here, I would have 0 equals log base b of x plus 3. I can't calculate this because I've got a base of b. In order to calculate, I would need a value for my base. So I know that my x-intercept exists. I know it's going to have to be between 0 and 1, but the exact value, I would have to have a value for b to figure out what that exact value would be. It's going to be a fraction, less than 1, but I don't know what the value will be. I know that I do have an x-intercept. Okay, last transformation. We've got two things going on here, two different transformations. This first one is a vertical stretch. Vertical stretch. What about this second one? Now, my pattern of transformation says x minus h. This is an x plus 4, which means I plugged in a negative 4, so I'm going 4 units back to the left. 4 units back to the left. All right. 4 units back to the left. Let's start with our vertical asymptote at x equals 0. If I shift that vertical asymptote at x equals 0, 4 units back to the left, from 0 I go 1, 2, 3, 4. There's negative 4 for my vertical asymptote. Vertical asymptote is now at x equals negative 4. The other thing I need to shift is my x-intercept 1, 0. I am not going up or down with it, but it is moving 4 units back to the left. 4 units to the left from 1. 1, 2, 3, 4. It is still my x-intercept, but now instead of at 1, 0, we are at negative 3, 0. And I can shape my function. Oh, wait. Vertical stretch. What's going to happen with my vertical stretch? If I take this and I stretch it up, it's going to get steeper, isn't it? So let's draw that steeper. And I'm not going to stop. I know I'm going to have a y-intercept here, but I'm not going to stop and calculate it because I don't have a value for b. I don't know exactly what it would be. Now, range, all real numbers, is all real numbers, is all real numbers. That doesn't change. Domain, however, is limited by that vertical asymptote. My vertical asymptote now is at negative 4. So my domain in my function is from negative 4 to infinity. All right. We did it. We talked about what a log function is. We sketched graphs, used transformations, and we did a lot of calculations with logarithms. And we practiced the definition of log going back and forth from exponential functions to log functions. Great job. I will see you next time.